Okay, welcome to the mini lecture on critical thinking and statistics. We're going to cover just a handful of problems here, but they cover different issues, but at the same time related. They all deal with, in some way or fashion, statistics, but at the same time they deal with how to frame issues and how to think about issues and how to not necessarily fall for the most obvious answer, which our brains are sometimes hardwired to do. So we have the Linda problem, the Monty-Hall paradox, guessing on a standardized test, and we'll wrap it up with the Gaussian sum. So let's take the Linda problem. It turns out that we're not quite as good at evaluating statistics and in particular probabilities as well as you might think. We're simply not hardwired for it, I guess you could say, from an evolutionary point of view. I mean, for tens of thousands of years, we were hunters and gatherers. So we didn't really have to think about probabilities very much. We just acted on instinct. And the Linda problem kind of brings that to full view. All right, let's take a look at it. This problem was popularized by two gentlemen, Tversky and Kahneman. Both were psychologists. And Kahneman wound up winning the Nobel Prize, believe it or not, in economics. And Tversky would have won the prize as well had he lived to see the day. But in any event, this was the question that they asked in their laboratories. They asked students this, they asked just common everyday ordinary people on the street. So it says, Linda is a 31-year-old single, outspoken, and very bright person. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Now that last one clearly dates this problem because we haven't heard of anti-nuclear demonstrations until, you'd have to go all the way back to the 1980s. And as soon as the 90s rolled around and the Cold War was over, we haven't heard much about those kind of demonstrations. In any event, the question is very simple. Which is more probable? Remember the word? Probable. Which is more probable? Number one, that Linda is a bank teller. And number two, Linda is a bank teller and active in the feminist movement. So you might be wondering, what did most of the respondents answer? Well, the overwhelming majority of respondents answered number two, that Linda is a bank teller and active in the feminist movement. But we got to go back and think about what was that question. The question is, which is more probable? And when you step back and think about it that way, not in terms of what's plausible, that's a different kind of a question, but what is probable? That has very specific meaning. Well, think about it in terms of heads and tails. If you just flipped a coin once, flipped a penny once, and you ask the question, what's the probability of getting heads? Well, you know what that would be, 1 over 2, 50%. If I ask you another question, however, that is, what's the probability of flipping heads now and also heads the next time? Heads 2 times in a row. Well, those are two separate events. When you're interested in two separate events happening, then you have to multiply their probabilities times each other. So that means the probability of rolling a head, the heads once for a penny is just 1/2. But the probability of rolling heads 2 times in a row is 1/2 times 1/2, which is 1/4, which is smaller than the original probability of just flipping heads just once. Well, it's the same thing here. All right, in fact, if you wanted to think about it in terms of a Venn diagram, you could think about Linda as a bank teller, it's one circle, but then another circle, which would be a smaller circle, of all the bank tellers, how many of them are in the feminist movement? Well, that would be a smaller number, right? It would be a smaller circle. In other words, that first big one would be number 1, Linda's a bank teller, and the one inside would be number 2, Linda's a bank teller and active in the feminist movement. And we can see right away that that couldn't possibly be right. Now, just so that you don't think this is all just one big slam dunk, this has generated quite a bit of response in the literature in psychology and how to set up experiments. And in fact, some of the critics just argue, well, it's in the wording, because people's understanding of what probable means might be interpreted to mean plausible. And of course, certainly the second one is plausible, given what you know about Linda in the narrative. But that really wasn't the question. The question was baldly stated as probable. The other thing is, experimenters have tried to get around that by not doing that, and that is giving lots of other choices. And even when you give lots of other choices, still that answer rose to the top, that Linda's a bank teller, plus she's also active in the feminist movement, beating out lots of other probabilities that clearly have to be a lot higher probability than the one that was chosen. So anyway, that just kind of gives you an idea that we're not really hardwired for probabilities and thinking about them correctly, and we need to kind of get a more cooler head. All right, the second one is known as the Monty Hall paradox. And this was popularized by a very famous woman by the name of Marilyn Savant. And I know that's not a household name necessarily, but she was married to a very famous physicist. She was bright on her own, all by herself without her husband. But she was married to Carl Sagan, who was a physicist, I believe, at Princeton. And she wrote an article, I believe it was in Parade magazine or Reader's Digest, in which she invited readers to answer a question that she had. And it was based on a very popular TV show, which most of the readers had probably watched. And the way it worked on the Monty Hall show was you had all these contestants guessing at various prices for things, and if you got really close to the price, you would win. And you kept going to various stages. And if you wound up being the final contestant, you had this grand prize that you could win. And what they would do is that they would have these doors. Door number 1, door number 2, and then door number 3. And then Monty Hall would say, pick a door. One of them has a car behind it, and 2 have some kind of gag prize, like a goat. So you go ahead and you pick door number 1. And then Monty Hall does something really neat at this point. It increases the drama. He goes ahead and opens up one of the other doors. So he opens up door number 2, and sure enough, there's a goat. He never opens up the door to reveal a car, okay? I'll just let you know that. That would spoil the whole thing. It would be anticlimactic. But then he does something interesting. He says, okay, you've chosen door number 1. I've opened door number 2 and revealed a goat. I'm now going to give you a chance to switch to door number 3 if you wish, or you can stick with door number 1. So Marilyn Savant asked this question in that column to her readers, and that is, she asked, what is the probability of winning the car if you switch? The overwhelming majority of readers said 1/2. That is, it's a flip of a coin. It's a 50-50 chance. 50-50 if she stays where she is, 50-50 if she decides to switch to door number 3. But as Marilyn Savant explained, that answer couldn't possibly be right. And the reason why it can't is because of an elementary ironclad law in probabilities, and that is all the probabilities of a particular event have to all add up to 1. So for example, you're thinking about throwing a die. If you throw a die, what's the probability of getting just a 1? Well, it's just 1 out of 6. What's the probability of getting a 2? 1 out of 6. Probability of getting a 3? 1 out of 6, etc., all the way to 6. And what's true about all of those individual probabilities? What do they add to? Well, a 6 plus a 6 plus a 6, you get it all the way up to 1/6 for rolling a 6. That adds up to 6/6, which is 1. But if you think about it, if you're giving an answer that this is a half and this is a half, well, those add up to 1. But then that says that the probability was 0 for door number 2, which of course can't be right? Because that had a probability of being picked, correct? So let's back up. What were the chances that you were going to pick a goat in the beginning? Well, it would have been a 2 out of a 3 chance. 2 of the doors had goats. 1 didn't. So it's more likely you picked a goat door. Not for sure, but more than likely. And so if you switch, it's more likely you win the car. Because what are the chances are that you picked the car in the first place? The chances that you picked a car in the first place were only 1 out of 3. So if you switch, right, you have a 2/3 chance of getting it, you know, 2 out of every 3 times that you play this game. Now, a number of people wrote in indignant saying this can't possibly be right. It's clearly a coin toss. She doesn't know what she's talking about. All the way up to the point where one of the smartest mathematicians in the country, who had actually won the Field Medal, which is the highest medal or award you can win. It's sort of like the Nobel Prize in economics, only for mathematicians. And in any event, this fellow told Marilyn Savant, you know, you really shouldn't be talking about mathematics and statistics because you don't know what you're talking about. Well, after she provided a very detailed proof that was pretty ironclad, in the end, this guy had to write a letter of apology in the column just saying, you're correct, and I'm sorry, mea culpa, right? All right, so when really, really smart people like that mess up on probabilities, the rest of us can sleep a lot better. But it does tell us that we shouldn't be too confident about our ability to do these things. And that has all sorts of ramifications, particularly with regard to our investment decisions in terms of picking stocks or bonds, or whether to be in the stock market at all or the bond market, or what should be our appropriate mix between the two, and how likely it is for there to be a complete collapse of the stock market, or at least a correction. Turns out we're just not really good at thinking about those things. All right, the third one deals with guessing on a standardized test. Now, in the old days, the SAT used to penalize guessing, but they penalize a particular type of guessing, that is random guessing. They didn't want to penalize educated guessing. Now, it turns out the new SATs come out and they don't do that anymore. But the way it worked is this. It would be 9 times the number correct minus 5 times the number wrong and 0 for unanswered, meaning you weren't penalized if you didn't get it right, but as long as you left it alone, it was just 0, but you didn't lose any points. So if you imagine that on the SAT there are typically 5 choices, A, B, C, D, and E. The question is, how many would you have to eliminate for it to be rational to engage in guessing? Well, let's say you don't have any eliminated. Well, that would be bad news. But how do you know for sure? Well, what it is it's an expected value. It's the probability times the payoff plus the probability of not getting it right times the penalty, and that equals the expected payoff. So in plain English, what's the chance you were going to get it right the first time? 1 out of 5, because you have no idea which ones are right or wrong. So 1 out of 5 times a payoff of 9. Great. But minus, because it would be a penalty, 5 times, I'm sorry, I shouldn't have written 5, should have wrote the probability. The probability of getting it wrong would be 4/5 times 5. And of course, I already had the minus sign there, so you think about that as -5. You could add -5. It doesn't matter which way you do it. Either way, that's negative. So what do you have? 9/5 minus 20/5. And it's pretty easy to see. You shouldn't be guessing on these problems, because every 10 that you get wrong, every 10 that you do this way, you're going to be losing 11 over 5 points, which is a little bit more than 2 points for each problem. So not a great idea. But what if you've eliminated A? You know that A is incorrect. Let me make that more emphatic by just like drawing an X through it. Well, the payoffs are still the same. That's still negative if you get it wrong. But the probabilities change, right? So let's do those. Probability of getting it right now has gone up. It's now 1 out of 4 that you'll get it right, and it's 3 out of 4 that you'll get it wrong. So this is really what? 9/4 minus 15/4, and what is that? Minus 6/4, which is minus 3/2, which is minus 1.5. So again, every 10 problems that you do like this, you're going to lose 1.5 points on average. Not on every single one, because some of them you'll get right just by luck. But on average, that's what you'll lose. So that's not good. So let's examine what happens if you eliminated 2. Again, just go in and change the probabilities. There's an easier way of solving this problem, by the way, using algebra. But I don't want to do that because I don't want to take away from the intuition behind what's going on. All right, so what would be the probability of getting it right? Well, now it'd be 1/3. The probability of getting it wrong would be 2/3. So this is 9/3 minus 10/3. It's razor thin, but it's still negative, right? And so that means for every 10 problems, on average, you're going to lose 1/3 of a point, and that's going to mean roughly about 3.33 points subtracted for every 10 problems that you engage in guessing. So still not a bright idea. Now let's assume you've eliminated 3 of them. Well, this now turns to 1/2. This turns to 1/2. And now what do you have? Well, let's work it. That first part is 9/2, and the second part is 5/2, and that's equal to 4/2, which is equal to 2. So on average, when you have problems like this where you've been able to eliminate 3 of the answers, your expected payoff is going to be 2. You're going to get some of them wrong, but on average, you're going to get 2 points over the long haul, and that means it's rational to engage in guessing here. All right, that pretty much rounds out that part of the standardized testing. And then I want to talk just about one more, which is the Gaussian sum. This is more about creative thinking and also about what I would call getting your hands dirty, which is a very good technique to use when you're problem solving. That is, when you don't have a formula or you don't really have an approach to a problem, you're not really sure where the problem's taking you. All right, so this particular example that I'm going to bring to you is probably apocryphal, but it's believable. It's about Frederick Gauss when he was about 10 years old. And there's been lots of different versions of this story, but I've heard it in so many different ways that I think there's probably some element of truth in this story. Gauss, when he was 10, was very precocious. He knew all the answers. He was always raising his hands to answer the professor's questions, the teacher's questions. And after a while, this really got on the teacher's nerves. And so the teacher said, I'm going to fix Frederick real good. So I'm going to send him to the other room. I'm going to have them work on this problem that will keep him occupied and out of my hair. And so he said, Frederick, I want you to add up the numbers 1 through 100. Now, he knew this wasn't a hard problem per se because, you know, obviously Frederick can add. But it's a time-consuming problem, and that he's going to be there a while. But it turns out he wasn't there for a while. He was there for about 15 seconds, and he came back with an answer, and he goes, I already know the answer. The answer is 5,050. And of course, his teacher was absolutely incredulous. Of course, he knew that that was the right answer. But he says, well, how did you know that was the right answer? And he goes, well, I just started playing around with the numbers. I started listing them, 1, 2, 3, 4, blah, 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 and I listed all these, and I got 97, and 98 and 99 and 100. And then what I noticed is I started just adding up pairs. I said, let me just add number 1 with 100, and that becomes 101. And if I add 2 and 99, that's 101, and 3 and 98, and that's 101, and 4 and 97, and that's 101. And in fact, if there's 100 of these numbers and I've got all these pairs, it means I've got 50 pairs. So all I have to do is multiply 101 times 50. Well, I know what 101 times 100 is. That's 10100. All I got to do is cut that number in half, and that's a 5,050. And that's exactly what these numbers sum to. In fact, it's true about any list of numbers, which comes in real handy. In any event, you're probably thinking to yourself, I'm no Gauss. I'm not going to make a discovery like this. You're probably right, but that doesn't mean that you can't use your powers of intuition and also just your ability to just play around and fool around with stuff, getting your hands dirty, trying stuff. And some of the stuff that you'll try won't work, but sometimes it will. In any event, that's what critical thinking is all about, really tearing apart a problem, getting to the heart and soul of it, and not have the problem beat you, right? It's certainly true that you're going to go through some struggles and a little bit of blood, sweat, and tears, but in the end, there can be a nice payoff. So anyway, I hope you enjoyed this little mini lecture, and until next time, we'll see you then.